Taylor series, which is a specific kind of infinite sum. So first off, I want to start out with this more general definition of power series. A power series centered at x equals a is a series of this form, so infinite sum, and from 0 to infinity. There are some coefficients, which we'll call c's. They are constants. This center here, centered at x equals a is some constant, a number. So we have x minus a to the nth power, and then multiplied by some coefficient. So this power series is a function of x. X is a variable here. The domain of this function is all those values of x for which this series converges. And there's always at least one number in the domain of a power series, and that's when x equals a, and then all of these terms here are 0, and so you just get that it equals c sub 0. This is sort of like a polynomial with possibly infinite degree. If there's a point where these coefficients are 0 from that point on, then you have an actual finite polynomial. If these coefficients are not 0, there's always some powers available forever. It's sort of like a polynomial with infinite degree. One of the nice things about power series, as opposed to other series in general, is that it's really easy to take their derivative or their integral. So just like a regular polynomial, if you take the derivative of one of these power series, you can take the derivative of each term individually and then add them up. That's just the sum rule. If this is a finite sum, a sum rule for derivatives, but this is an infinite sum, and it still works. Now, it doesn't work for every single series out there, but for power series it does. Same thing with integrals. If you want to integrate a power series, and I just realized I forgot the dx, I'll have to add that later. Then you need to, well, you can interchange the sum and the integral, so you can integrate each piece one by one. An example of a power series is a geometric series. Now, not every power series is geometric, but geometric series is a power series where all of the coefficients are the same. That's what makes it geometric. So this is geometric series centered at 0, so a equals 0, and all the coefficients c are equal to some c sub I is equal to c for all I. So we know what this converges to. We saw that last time. The geometric series with initial term c and common ratio x here is in place of the common ratio r, is equal to c over 1 minus x, as long as x is in this range of values. Otherwise, that series diverges. So in other words, this series here is a function. Its domain is -1 to 1, and on that domain, this series happens to be the same as this function c over 1 minus x. So that raises the question, are there other functions that are equal to the sum of some power series, at least on the domain where that series is defined? So in other words, if we're given a function f, can we find coefficients, these c's, so that f of x is equal to this sum of this power series? All right, that is called a Taylor series in that case. The process of representing a function by a power series is called expanding the function into a series. And that power series is called a Taylor series after a mathematician named Taylor who lived a long time ago. Expanding functions into Taylor series and taking their derivatives and integrating them had quite a few applications then. We don't often see it so much anymore. But you can use Taylor series to approximate things like pi and e. Those are irrational numbers that are hard to get at. Back then they didn't have a calculator that would tell you the value of pi to as many decimal places as you wanted. Logarithmic and trigonometric functions often have irrational values that come out, difficult to calculate, but when you expand these into Taylor series, you can at least approximate them. The partial sums of a Taylor series are actual polynomials, and so you can approximate these functions using partial sums of the Taylor series. Fortunately, finding the power series that represents a given function is fairly straightforward if that function is repeatedly differentiable. So you can take the derivative, the second derivative, the third derivative, and so on forever. And the idea here is to find all those derivatives and then plug in the center, x equals a. Remember, a is the center of the power series, which we kind of get to choose at the beginning. So if somehow we have this function f equals to this power series, our goal is to see what coefficients do we need in order to make this equation work. So we're going to take the mth derivative for whatever m, and we're going to plug in x equals a. So because we can differentiate term by term here, the mth derivative of this Taylor series would be the series where you add up the nth derivative of each term and then plug in x equals a. We want to figure out what these derivatives are. Okay, if n is less than m, so n here is the index on this sum. If n is smaller than m, all right, we're taking, say, for example, n is 10 and m, the derivative, is 15. We have a 10th degree power function here, and we got the 15th derivative. That derivative is going to kill off that power. You just apply the power rule over and over and over again. Eventually, you're going to get to 0. So whenever n is smaller than m, the nth derivative of this nth power will give us 0. And plugging in x equals a, it's still 0. So anything less than the order of the derivative gets killed off to 0. If n is bigger than m, then the derivative will not kill off that power. So each time you take the derivative, the power will get reduced by 1. So you take the derivative m times, you'll get n minus m. And since n is bigger than m, this is positive. So there's still some x minus a here. Now there's this coefficient you get. You keep, when you do the power rule, you keep taking down the power. We don't really care about that because we're going to plug in x equals a. And we're going to plug in x equals a right here, and we're going to get 0 in this spot. Okay, here's a minus a. So it doesn't matter what this coefficient is, it's multiplied by 0, and so that's 0. Anytime the index in our sum, so the power here on our term, if that's bigger than the number of the derivative, we also get 0. The only time we don't get 0 is when n and m are the same. So we have the mth derivative and we have the mth power here. So n and m are identical. That means that as you reduce the power by 1 each time, you get down here to the 0th power, and you get then that this mth derivative is n factorial times c sub n, or m factorial times c sub n. Here n and m are the same. That's the only time you don't get 0. So the nth derivative of that Taylor series, which is the nth derivative of the function because they're equal, that nth derivative is m factorial times the mth coefficient. And that means you divide both sides by m factorial. The coefficient, the mth coefficient, has to be the derivative of the function, the nth derivative of the function, plug in the number a, divide by m factorial, and that's it. So, in other words, if a function has derivatives of every order, and if that function can be represented by a power series centered at x equals a for some interval I, that power series has to be this one. Infinite sum, the nth term is the nth order derivative, plug in the number a, divide by n factorial. That's the coefficient on x minus a to the nth power. And the interval I is just the interval where this series converges, which has to have at least the number a in it, but could have more stuff. Now, there's an important if here, if the function can be represented by a power series. Now, there are some functions with derivatives of every order, and this series so that exists, and it converges sometimes, but the function isn't equal to it for whatever reason. We're not going to deal with functions like that, but it is an if. If a function equals a Taylor series, this is the one it has to equal. All right, here's an example of that. So the function I want to look at is e raised to the x power. I'm going to center this at x equals 0. And just a side note here, Taylor series centered at x equals 0 are also called Maclaurin series after another mathematician. So we know the derivatives of this function, no matter what number derivative, what order derivative, they're all e to the x. And e to the 0 is 1. So we're going to remember, we're going to take the nth derivative of the function and we're going to plug in the value of the center. The center here is 0. So this is, if I go back up here, this is the f, the nth derivative of f, and then plugging in a. That's this part. That's 1. And we're going to need to divide by n factorial, and that gives us the nth coefficient of the Taylor series is 1 over n factorial. So if f of x equals the sum of its Taylor series, then this is the series it has to be. And it turns out, which I'm not going to prove, that for this particular function, this Taylor series actually does converge for all x. So no matter what x is, this series converges and is equal to e to the x. So e to the x is equal to, all the time, for all x, the sum, n equals 0 to infinity, of x to the nth power divided by n factorial. Okay. Partial sums of a Taylor series, as I mentioned, are actual polynomials. So if you don't have an infinite sum, you cut this off somewhere, then you get an actual polynomial. So they're called Taylor polynomials. Here's the Taylor polynomial. I said of degree m. I guess I should say of degree at most m, because it's possible that some of the coefficients might be 0. So you might not have every power here. We'll see that later. We can approximate a Taylor series to whatever level of accuracy we want by using a Taylor polynomial. The higher the degree we make, the better the approximation is. And if this Taylor series is going to converge, that means that the terms need to go to 0. So from m on to infinity, it has to be a pretty small amount. The terms have to be getting smaller and smaller. So the higher the degree is, the more of the meat of the series you have, I guess. All right. Notice the Taylor polynomial of degree 1. So we'll just have the 0 term and the 1 term. And what we get, just plug that into the formula. Here's what comes out. F of a, that's the 0 term. And here is the degree 1 term, f prime of a times x minus a. That's the formula for the tangent line. So the tangent line is first degree Taylor polynomial for a function. And so Taylor polynomials are really generalizations of the tangent line up to higher degrees. In fact, if we look at degree 2, we get, or you can follow all this through, this is the final result. It's the tangent line plus this quadratic piece, f double prime of a over 2 times x minus a squared. This formula might look familiar to you. We covered that in Calculus 1. We did quadratic approximation. In fact, we did linear approximation and quadratic approximation together in one lab. Linear approximation is the tangent line. Quadratic approximation adds on this little quadratic piece. And that happens to be Taylor polynomial of degree 2. So you really have done this before. We're just now adding higher degrees. All right, so we're going to approximate the value of e using Taylor polynomials. So as we saw above, e to the x is this series. The Taylor polynomial of degree m looks like this. So e to the x is approximately the sum of this polynomial. You just take the power of x and divide by the factorial of that same power. The bigger m is, the better our approximation will be. To approximate e, we're going to plug in x equals 1. E to the first power is e. And if you plug in x equals 1, all these are 1s on top, and you get e is approximately 1 plus 1 plus a half plus a sixth, so on, just adding up the reciprocals of all the factorials. So I set up a little interact so we can apply this formula. So here is the degree 1 Taylor polynomial. So there's the tangent line. That would approximate the value of e to be 2. And here's the actual value with 30 decimal places just for comparison. If we go to the quadratic approximation, whoops, what went wrong here? okay. I'm not sure exactly what happened there, but it seems to be working okay now. I just reran this and it seems to have fixed whatever little hiccup was going on there. So anyway, the degree 2 Taylor polynomial quadratic approximation gives us 2.5. So you see we're kind of getting closer. So let's change this to 3. Now we got 2.6 repeating, so 2 2/3. We're getting closer. Here's degree 4. Now we got 2.7 and degree 5 polynomial. We got the first 2 decimal places now, 2.71. Let's skip up to degree 10. And you can see now our approximation of E is correct to 1, 2, 3, 4, 5, 6, 7. 7 decimal places agree here. Let's go up to 15. And we've added a few more decimal places. Now we're good to this one. And how about 20? And let's see, right here is where they agree. How about degree 30? Well, by the time we get to degree 30, they agree on all of these. We didn't need all 30 to get all those. Oh, 25 wasn't enough. Looks like right to here they agree. Just kind of curious, what's the smallest degree we need? Almost, we're right here at the end. Degree 27, that's enough. So if you want 30 decimal places of E, you can use a degree 27 polynomial, and that'd be quite a monster fraction to actually compute this thing out by hand. But you would get exactly the right value, at least at 30 decimal places. Alright, now I'd like to look at some graphs. So here we have e to the x in black, along with 3 of its Taylor polynomials. In blue is degree 2, it's a parabola approximation, and degree 3 in green, and degree 4 in red. So this is all centered at 0. So right here at x equals 0, they all agree. It's sort of like the point of tangency of the tangent line. As you move away from 0, the approximation gets worse. So the center, closer to the center of this expansion is better approximation. And you can see as the degree goes up, so this is degree 2, degree 3, degree 4, as the degree goes up, the approximation gets better. The curve starts to match closer and closer and closer. So by the time you get to degree 4, you see this red line, it's pretty close to the black line. Now we're in a pretty small window here. We're just going from -1 to 1. And these are not exactly the same, but pretty good approximation for just degree 4 polynomial. I'm going to change the x min and max a little bit. Same degrees here, same picture. I just zoomed out. So before I was just looking between -1 and 1, so I was right in here. As I go out farther away, I see, okay, this doesn't work forever. This is e to the x, so we have this exponential which rockets up really fast. Polynomials don't grow as fast as exponential, so here's the parabola which really starts lagging. The higher degree you get, the better. So you can see as the degree goes up, this polynomial starts growing more and more rapidly, starts bending towards e to the x. And if we had higher degree, we'd see it get even closer and closer and closer. Now on this side, we have an e to the x, a horizontal asymptote. It just goes along the x-axis. My polynomial, they go flying off, to infinity or negative infinity, which e to the x does not do. But the higher the degree, the flatter we get in here, and it kind of follows the x-axis for a longer time and matches that e to the x for a while. Alright, and then below we have this little animation. And I'm not sure how this will show up on the video. You might just run it on your own notes. We're going to see Taylor polynomials of increasing degree. Those will be in blue, with e to the x in black. So here's e to the x. Here's our kind of initial Taylor polynomial. I'm not sure which degree I started with. I'd have to look through this code and figure out where exactly I started this thing. I think I started with a tangent line and go up from there. So I think this one there is the tangent line, and the degree is going up, 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 and the higher the degree gets, oops, my video is freezing. The higher the degree gets, the more this Taylor polynomial bends up towards e to the x. And let's see, I stopped, this is degree 10. So this is kind of my degrees here at the end. So I went from 1 to 10. This is degree 10 polynomial. And what is my x-axis here? My x-axis goes up to 15. So this is 15. So it's a pretty broad range here in the x-axis. By degree 10, I'm bending pretty well up along through here. And of course, the higher I go, the better that approximation will be. Okay, we can use Sage to calculate Taylor polynomials. It has a built-in command. It's called Taylor. You need to feed that Taylor command four things: the function or an expression that you want to expand, and the variable of expansion, the center of the expansion, and then the degree of the Taylor polynomial you want. So, for example, the 10th degree Taylor polynomial centered at x equals 0 for this function e to the x would look like this. Taylor is the command, and then of course parentheses. Here's the function we're trying to expand, e to the x. Here's the variable, x. Here's the center, 0, centered at x equals 0. Here's the degree of the polynomial, 10th degree. And so here is our Taylor polynomial, and this is just 1 over n factorial times x to the nth power. So this is 10 factorial down here, 9 factorial, and 8 factorial, and so on. And it goes all the way down there. Here's another example. I want the 15th degree Taylor polynomials for sine of x centered at x equals 0, and centered at x equals minus pi, and centered at x equals pi. So I got 3 different Taylor polynomials here with 3 different centers. So here's the function is sine, the variable is x, the center here is 0, the degree is 15. And here is the answer that you get. Here's the same function, same variable, same degree. Now it's just centered at minus pi instead. And so for whatever reason, Sage here doesn't write this as x minus pi as we normally, x plus pi, we normally write that order. It puts the pi first. But anyway, this is x minus negative pi, which is x plus pi. And you can see here, and here's the one centered at pi. With the sine function, we actually end up with these coefficients are the same when I'm centered at pi or minus pi or 0. So if you kind of think about what the derivatives of sine are, it's either sine or cosine, and then with a plus or minus in front. And then you're going to plug in 0 or pi or negative pi to those things. And when you do, sometimes you get 0, and sometimes you get 1 or negative 1. And so that numerically we end up with the same thing. These happen to be the factorials. Like here, this coefficient is 1 over 9 factorial. It's the same thing as up here, the 9 factorial. And notice that in all of these, the odd powers show up, but the even powers do not. So it's certainly possible that you might have some coefficients equal to 0. In the case of these expansions of sine, you have that all the even powers end up coefficient 0. So, and then the odd powers are the ones that are here. It's not exactly equal to what's up here with e to the x. Notice e to the x, these are all positive. And here, these are it's the same number, except here's a negative, positive, negative, positive, negative, positive. So the signs alternate. Here's cosine, centered at x equals 0. And now I'm just going to do different degrees. Degree 5, degree 10, degree 15. So function is cosine, the variable is x, the center is 0, degree is 5. So here's our degree 5 polynomial. Actually, this is degree 4 polynomial because the coefficient is 0 for the 5th power. And like with sine, only the odd power showed up. With cosine, only the even power show up. It has to do with what the derivative of cosine is, and when you plug in 0, you get either 0 or 1 or minus 1. Here's the 10th degree, and notice here that this 4th degree is right here at the beginning of the 10th degree. So these degrees, I mean, they're just adding extra terms. It doesn't change anything at the bottom. So here these first 3 terms are still there, and then you're just adding higher powers. Here's the degree 15, Well, this is degree 14, of course, because the x to the 15th has coefficient 0, so that doesn't actually show up. The numbers down here, like this is, down here is 8 factorial, this is 6 factorial, this is 4 factorial. So just like with sine and with e to the x, we end up with just 1 over the factorial of the power. Just like with sine, we have alternating signs here, minus plus, minus plus, minus plus. So it's almost like if you could deal with these signs somehow, you could just add together sine and cosine, and you would get this e to the x. E to the x has all exactly the same terms as sine and cosine together, just with kind of the signs are wrong. And if you sort of used imaginary numbers, you imagine putting an I in here, where you raise I to various powers, and you could cancel out this minus sign potentially. There's a way where you can kind of use imaginary numbers and stick them in here, and you could get that e to the x is some sort of sum of sine and cosine. I won't go into that, but it's kind of interesting to think about. Not immediately obvious at all by looking at the functions, but when you look at their Taylor series, it seems very suggestive there. There's some sort of relationship between sine and cosine and e to the x, it looks like. Alright, example 7, the 10th degree Taylor polynomial centered at x equals 0 of this function, c over 1 minus x. So I told Sage that c is a variable. I did the Taylor command, c divided by 1 minus x. X is the variable of the expansion. That means c will be treated as a constant rather than a variable. Centered at 0, degree 10, and here it is. Remember, this is the Taylor series for, or rather, the Taylor series for this function is the geometric series. So this is partial sum of the geometric series, where you just have the constant here, which is the first term, and then x is the common ratio. Here's a graph of that one when c is equal to 1. So 1 over 1 minus x, and is in black, and then the in blue is the Taylor polynomial of degree 10 for 1 over 1 minus x. And you can see that at least near the center of 0, this is looking pretty good.